This is part 10 in our series of lectures on section 2.5 dealing with other forms of induction. We're continuing our lectures that deal a little bit with the subject of algebra. In this lecture we're going to talk a little bit more about greatest common divisors. We'll introduce the idea of relatively prime integers, and we'll prove a result which is known as Euclid's lemma. Two natural numbers, a and b, are said to be relatively prime if their greatest common divisor is 1. In other words, the only natural number that divides both of them is 1. Here are some examples for you. 8 and 21 are relatively prime. Of course, neither of them is prime, but the only natural number that divides both 8 and 21 is 1, and so they are relatively prime. On the other hand, 21 and 14 are not relatively prime because 7 is a natural number that divides both of them. Now I want to recall some results that we established in an earlier lecture dealing with greatest common divisors. First of all, the greatest common divisor of any two natural numbers always exists. And a non-trivial result that we proved about it is that the greatest common divisor of a and b is the smallest positive integer combination of a and b. So in particular, it is an integer combination of a and b. In other words, there exist integers m and n such that the greatest common divisor of a and b can be written as ma plus nb. And so if a and b are relatively prime, that means that their greatest common divisor is 1, and therefore there exist integers m and n such that ma plus nb is equal to 1. Now this fact here that if two integers are relatively prime, or if two natural numbers are relatively prime, that one can write them in this way, that turns out to be quite an important result. And I'm going to show you an interesting application of it later on in this lecture. So it's an interesting question to see if you can actually calculate these integers m and n in case a and b are relatively prime. Well, 4 and 3 are examples of relatively prime integers. Do you see how to produce the m and the n in this case? Well, that's pretty simple because you can see by inspection that 4 minus 3 is equal to 1. So we can take m to be 1 and n to be minus 1. Here's another pair of relatively prime integers. Do you see how to construct the m and the n in this case? Well, this is also fairly simple because 3 times 2 minus 5 is equal to 1. And so there you see how we can find an integer combination of 3 and 5 that adds up to 1. But with 12 and 41 are also relatively prime, but it's not so easy to see how to come up with the m and the n in this case. In fact, if you calculate 41 times 5 minus 17 times 12, you'll see that that comes out to be 205 minus 204, which is 1. So you might wonder how I came up with the coefficients 5 and minus 17 in this case. There's actually an algorithm which is known as the Euclidean algorithm that makes use of the division algorithm in order to figure out how to come up with this m and n. So let me do an example for you that demonstrates the use of this Euclidean algorithm in order to come up with this 5 and this 17. I think it's worth doing because it makes you look a little bit more closely at the division algorithm. So here's the calculation. What we do is we begin with 41 and 12, and we apply the division algorithm in which 12 is the divisor. So dividing 12 into 41, we get a quotient of 3 and a remainder of 5. 36 plus 5 is 41. Now what you do is you apply again the division algorithm, this time with 12 and 5, in which we use 5 as the divisor. 12 is 2 times 5, and that leaves a remainder of 2. Now you repeat again, you take 5 and 2, and you apply the division algorithm to those, and you get 5 is equal to 2 times 2 with a remainder of 1. The fact that we got it down to 1 is actually a statement of the fact that 41 and 12 are relatively prime. Now what you do is you go backwards from here. You write 1 as 5 minus 2 times 2. Now this 2, this red 2, actually came from being the remainder in this calculation here. So I can replace this 2 by 12 minus 2 times 5. And that's what I've done here. Now I group the terms. I put all the 5's together. There's 1 5 here, and there are 2 times 2, 4 5's there. So that's 5 5's. And we have minus 2 times 12. Now this 5 here, that showed up as the remainder in the first calculation, and so we can replace it by 41 minus 3 times 12, which I've done here. And now just collect all of the 41's and the 12's separately. We have 5 41's, and we have minus 15 minus 2 12's, that's minus 17 12's, and that's the answer. That adds up to 1. So that technique actually works for any pair of relatively prime integers. In fact, it works for any pair of integers at all, where the last number that appears here is going to be the greatest common divisor of those two numbers. I'm going to close this lecture with a consideration of a theorem which is known as Euclid's lemma. We let a and b be natural numbers and p a prime. We suppose that p divides the product ab. Then the conclusion of Euclid's lemma is that p must either divide a or p must divide b. Now this is actually a theorem that we've considered in an earlier lecture a long time ago, and we considered it as an application of the fundamental theorem of arithmetic, which deals with factorization, prime factorizations of natural numbers. So here I'm going to show you a more elementary proof, one that doesn't make use of prime factorization. Okay, here's the proof. We let a and b be natural numbers and p prime. We suppose that p divides the product ab. Now we have to prove that p either divides a or p divides b. Well, if p divided a, then we would be finished. And so let's suppose that p does not divide a. Then we have to prove that p divides b. Well, since p doesn't divide a, since p is a prime, the only natural number that divides p at all is 1 and p, and therefore the only natural number that can divide both p and a is 1. So it follows that p and a must be relatively prime. Now we're going to use the fact that we established earlier on in the lecture, that there exist integers m and n such that ma plus np is equal to 1. Right? The 1 is the greatest common divisor of a and p. Now if you multiply this equation by b, you get ma times b plus np times b equals b. Now look at the terms in this equation that are divisible by p. We've assumed that p divides ab, and obviously p divides p. Therefore, p must divide any integer combination of a, b, and p, and so it must divide this whole thing. But this whole thing is equal to b, and so p divides b. And that completes the proof. Well, we're going to revisit this Euclid's lemma shortly, because it turns out that this is what's needed in order to prove the uniqueness part of the fundamental theorem of arithmetic, which says that there's exactly one way to write a given natural number as a product of primes. So we'll return to this at a later time in order to complete the proof of the fundamental theorem of arithmetic.